The equation for the pressure of an ideal gas is P equals 2/3 N, which is the number of molecules, over V, which is the volume of the container, times 1/2 mv squared. And this V is the velocity of a molecule. This is the mass of the molecules. This is the volume of the container. And N is the number of molecules. And P is pressure. So this is saying that pressure is proportional to the number of molecules per unit volume and to the average kinetic energy of the molecules. So we know that molecules have kinetic energy, and we can use that information to determine the temperature of the substance. So if we have this equation, we can compare it to the equation of the state for an ideal gas. And that involves a constant called the Boltzmann constant, and that is a little lowercase k with a sub b. And that is equal to 1.38 times 10 to the negative 23rd joules per Kelvin. So now we can say that pressure times volume for the ideal gas is equal to the number of molecules times the Boltzmann constant times the temperature. So using this information, we can set both PVs equal to each other and solve for T. So T is equal to 2/3 times the Boltzmann constant times 1/2 mv squared. So I use the equation from the first page and then this equation, set these equal to each other, and then solved for the temperature. So this is saying that the temperature is a direct measure of the average kinetic energy of the molecules. So, why is this important? Well, the only reason we can measure temperature is because we are actually measuring the average kinetic energy of the molecules. When things reach thermal equilibrium, the kinetic energy of one substance has excited the molecules in another. So if we're using a thermometer, we stick it into hot water. The hot water has a lot of kinetic energy. It gets transferred to the thermometer. The liquid inside the thermometer gets excited, has more kinetic energy, and rises. So, now what? We could rearrange this if we wanted to solve for the average kinetic energy per molecule. So if 1/2 mv squared is equal to kinetic energy, then we can actually rearrange, bring this term to the other side, and solve for kinetic energy. So 1/2 mv squared equals 3/2 times that Boltzmann constant times the temperature of the substance. So this is just talking about an individual molecule. Well, what if we wanted to know the total kinetic energy of n number of molecules? Well, the energy would be equal to n times 1/2 mv squared, which then you could say that that's also equal to 3/2 times n times the Boltzmann constant times the temperature, which conveniently, you guys have heard this so many times, PV equals nRT. Well, if that's the case, then this whole term is also equal to 3 halves times the number of moles times R times T. So it's important to know what the speed of a molecule would be for a given temperature or a given number of moles. And so what physicists use often is what's called the root mean square. So they actually take the equation that we just had and solve for the velocity. But they title it vrms, and that RMS stands for root mean square. So they want to find basically the speed or the velocity of molecules in a substance. So if we rearrange both those equations from before, we would get the square root of 3 times the Boltzmann constant times temperature over the mass, which is also equal to the square root of 3 RT over M, which this is the molar mass in kilograms per mole. So this is basically saying that at a given temperature, lighter molecules move much faster on average than heavier molecules. So for example, hydrogen with a molar mass of 2 times 10 to the negative third kilograms per mole has molecules moving 4 times as fast as oxygen, whose molar mass, so this is hydrogen, of oxygen, whose molar mass is 32 times 10 to the negative third kilograms per mole. So the RMS speed is not the speed at which the gas moves around the room, because such a molecule undergoes several billion collisions per second with other molecules under standard conditions. So the root mean squared kind of gives us an average that is actually useful in experiments. And in the book is a table that discusses some RMS speeds, or root mean square speeds, of different gases, and so it gives you the molar mass and the velocity at a given temperature will give you the root mean square velocity of the molecules. So, okay, who cares about all of these equations if you can't use them? So let's do an example problem. So a tank contains 2 moles of helium gas at 20 degrees Celsius. Assume that the helium behaves as an ideal gas. So find the total energy of the system. So we know that N equals 2.0, and T, because we need to transform that into Kelvin and add 273, so our T is actually 293, because 273 plus 20 gives us 293 Kelvin. And all we need to do is plug it in to our total energy equation. So the total energy is 3 halves times the number of moles times R times T. And remember, R is a constant. So if we plug in everything that we have 3 halves times 2 times 8.31 joules per mole Kelvin times 293 Kelvin. And we get an answer of 7.3, so that's a 7.3 times 10 to the third joules. So that is the total internal energy of the system. But what is the average kinetic energy per molecule? So we'd need a different equation for that so that we can solve for the per molecule kinetic energy. So if we use our equation that says that our kinetic energy, 1/2 mv squared, is equal to 3 halves times the Boltzmann constant times the temperature, then we can solve for the average kinetic energy per molecule. So if we plug in the Boltzmann constant, we have 1/2 mv squared equals 3/2 times 1.38 times 10 to the negative 23rd joules per Kelvin, remember that's a constant, times 293 Kelvin. We get that this whole term, the average kinetic energy per molecule, is 6.1 times 10 to the negative 21 joules. So think about that. That's really small. This is an extremely small number, a small amount of energy per molecule, but the molecules as a whole have 7.3 times 10 to the third joules of energy. So using the fact that the molar mass of helium, if we were to add on to this equation, if we know that the molar mass, big M, is equal to 4 times 10 to the negative third kilograms per mole, we can determine the RMS speed for the atoms at 20 degrees Celsius. So that is your question or your assignment for tonight, is what is the RMS speed of the atoms at 20 degrees Celsius. So come to class tomorrow with that answered.